Good morning, I'm Dan Wilson. I'm a science leader in cheminformatics from the Dow Chemical Company in Midland, Michigan. I'd like to thank Nicole and Oki and the meeting organizers for the opportunity to present some of our research this morning. And the title of my seminar is Computational Approaches to Acute Mammalian Toxicity. I'd like to acknowledge the principals in my immediate research group. The people that are highlighted in the photos, names are highlighted in blue, and we're a small group, but we're light on our feet. There are two goals to the research that I'm going to describe this morning. The first is to predict the acute toxicity using a computer of the three endpoints highlighted in blue, which would be oral, dermal, and inhalation systemic toxicity. Second, to predict the mechanisms of acute toxicity. And I'll have some slides highlighting why it's important to focus on mechanisms. So as an outline of my presentation, I'll describe something about the background of acute mammalian tox studies, review our generic computational approach with highlights on mechanisms with a few case histories of why we need to know them, application of our research on cholinergics, then some discussion on where do we go from here. So why focus on acute toxicity? Some obvious reasons. It's important for accidental exposure and poisoning, or intentional exposure even. Classification for labeling and shipping. Certain jurisdictions actually require it. REACH, China, EPA for pesticides, although that's changing in terms of some of the regs. And then for product stewardship, for personal protective equipment guidelines and internal exposure guidelines. And part of the reason we're focusing on this as a research objective is the thought that it should be easier to predict than some of the more complexities. The reason being that the AOPs would be more straightforward, and that there are actually more data with more compounds that would be available in the public literature. So a generic approach that we derived is to first assess commercial and free models, and quite honestly, if they work, we're a .com, we'd use them and we probably wouldn't follow up with a whole lot that falls below it. So, but they didn't, and I'll describe that. And then to focus on identifying mechanisms, assessing and building profilers, gathering data in vivo, in vitro, in silico, scaffolding. These are identifying distinguishing substructures, predicting the toxicity with docking, that's the interaction of proteins and ligands, and or regression, and then automating everything in KNIME workflows. And for the last part of this, I'll focus in reviewing how we actually applied this to some of our research finding on the cholinergics. When we assessed the available QSAR models, either ourselves or others that have assessed them, for acute toxicity, these are global models. So global meaning, ideally, you'd want to come along with any compound, be able to feed the structure into the model and have it predict toxicity by any route. And there's not a model that I'm aware of that does that adequately. And especially the thing that we'd worry most about is sensitivity, meaning would they correctly identify the most toxic compounds, and they don't. And they don't do it to a fashion that we'd feel comfortable with. And so we didn't know that when we started down this path, but we ascertained that. And we tried to start figuring out why and then what to do as a workaround. So when we look most closely at it, the real reason is there's just not enough data. So if we had a study on every compound known to man, there probably would be enough data to build models. And when we look at regional sets where they do have enough data, that's generally what we see a trend towards. But there's lots of different mechanisms and lots of different compounds. The other reason is that these QSARs use canned structural similarity searches. There's a number of them out there, and they're doing their best when you feed in a structure to try to find analogs that look closely enough, and then it uses those analogs to predict toxicity. But what we found is that most compounds are acutely toxic via interaction with specific receptors, and that subtle structural differences are important. The mechanistic targets are often unknown, and these QSARs weren't really trained against those mechanistic targets. So we started focusing on what those mechanisms were, and I'll talk a little bit about that. As an aside that will highlight the need to really focus on this, I'll give 4 quick case histories. Hydrocarbons, acceptors, some aliphatic fluorine compounds, and then some look-sees at OPs, which are organophosphates. So first with hydrocarbons, you can see here the classic way to first look at QSARs is to get a group of analogs that might be related to one of your compounds, to get their log KOWs, and then to do a regression plot and see what you get and see if it makes sense to predict the toxicity of the unknown. And here you see the R squared is 0.93. And in fact, for this subset of compounds, this would actually be a very valid approach to predict the toxicity by various routes. And you can build these models on the fly, either within the OECD toolbox, for instance, or you can build your own. I think we did this one in the toolbox. Another group would be acceptors. These are alpha-beta unsaturated compounds where when we look within a set, and by within a set meaning you could either pick conjugated aldehydes or conjugated acrylates or conjugated methacrylates, you find that within any one of those sets, if you do the same type of plot, you see, again, a pretty good R squared and the ability to predict the acute toxicity by any route. If you cross the different from an acrylate to a methacrylate to an aldehyde, that no longer holds true. And the reason the electrophilicity starts being a major factor in the model, but hopefully within any one of those sets, if you get enough data, you can still build your own model. And that's typically what we would do. Another example here would be aliphatic fluorines. So if you look at the general structure, you see an acid and a hydrocarbon chain with a fluorine at the end in various lengths. So if we try to predict the toxicity of this unknown using these analogs, you see the plot here, and these dots are the dots of the actual compounds. And then this is the compound here, and it would be predicted to have an acute toxicity of 2.1 milligrams per kilogram. However, the actual toxicity is over 100 milligrams per kilogram. So what's wrong with this picture? Typically, when we get outliers, we start beating our heads against anything to try to figure out what's going on. And part of what most people are doing in this field is gathering data that aren't their own, so from big public databases. So you have to trust the data or hope the data are curated or reliable. You start looking at the data, we start trying to understand, is that the issue? And that's what you would do here. But the other thing that we found is to really look at the mechanism. With something as subtly different as a compound where the only thing that is varying is the chain length, actually be that remarkably different in terms of the mechanism? Well, the answer is yes. And the reason for that is that the mechanism for this class of chemistries is actually understood, and that the parent smallest compound gets metabolized via the enzymes that are involved in the TCA cycle to a derivative that inhibits one of the enzymes of the Krebs cycle, and that is a kinase. And it basically stops the Krebs cycle dead in its tracks. That then stops the ability to produce energy, and the lack of ATP production lends to high lethality. And the interesting nuance of this, when I showed you the plot, I actually cherry-picked which compounds I put in there. And what you see is that the toxicity varies with the number of carbons in the chain. And so compounds that have even number carbons get metabolized through beta oxidation to the parent that will inhibit a kinase, and those with odd get metabolized to fluoropropionic acid, which does not. So typically, if you just had a various set of analogs, any group out there that's doing their first cut at trying to do something to predict toxicity, it's always a plot of log KOW versus tox. One would be totally misled in an instance like this. And that's an interesting example. Another example here, and this is a group of organophosphates. As I mentioned, we're focused on OPs. So here we plotted the inhalation toxicity versus the oral, and we see one flagrant outlier. And kind of building on the theme that I just described, is this outlier potentially due to some difference in the mechanism of this compound or not? So that the compound that is the outlier, its structure is shown here. When we take this structure and we feed it into freeware, and the freeware here is Toxtree, which has been pulled into the OEC toolbox, you can actually draw the structure, you press a button, and it tells us it's an OP, and then of high class, and which is important because we're plotting OPs. But when my techs and postdocs brought me that structure and I looked at it, I said, in fact, that compound is not an OP. And so I had them build our own profilers. And the criteria for whether an organophosphate compound will be highly acutely toxic or not is that it has to have the ability of acetylcholinesterase to try to attack this phosphorus. And when it does so, it hydrolyzes it. If you look at this compound here, this compound is essentially already hydrolyzed. It's a very highly acidic compound. That we modeled the pK, it's about 1.6. And so the difference in the acute toxicity when we plotted this by the inhalation versus the oral route is due to the fact that what we find as a theme is that compounds that are reactive are much more toxic by the inhalation route typically than by the oral route, which is what we're seeing here. And it's probably due to the fact that it's just a much more potent acid. It has nothing to do with it being an OP. And so the other thing I would mention, not to pick on the freeware at all, but when you take sarin, which is an OP, and you put it in the same profiler, it does not flag it as an OP. So that's part of the other reason. I think we had a gentleman give a talk from the military the other day where people that would be using in silico models to try to predict potential acute toxicity using some of the available areas, tools out there would be in trouble. So we built our own, and we're building our own further at that point. So our approach to mechanisms is to focus on highly acutely toxic compounds first, assume the number of mechanisms are limited, assume that most mechanisms are already known, and then we'll look them up in the literature and then start building our own profilers. And the way we've kind of systematically been going about this is to look at the chemistry, the phys-chem properties, look at tools to assess bioavailability in different pathways, and then look at the big databases of in vitro high throughput screening data, pull those into our databases. And a lot of these were generated by a robot at NCATS that ran the 10K library. And then to start building our own pathways where, if you've heard me lament about sitting in a Tim Hortons on a snowy Sunday with my computer and drawing all these out, that's a true story. But the nice thing is we then got these and we put them all behind our firewall into our databases, and we started looking at, is there any merit in that? And so the merit in that is if you can find one compound that inhibits one part of a pathway, you then understand something about the AOP and whether or not you can indict that pathway. So here we showed methotrexate, where we know that the AOP then is shutting down the ability to produce purines. We see the same thing with pyrimidines. So what we did in the old days, which was last year, we would take all of the substrate and product information from every one of these pathways, as well as by looking up by hand the enzymes, whether it was in the protein database, all the known in Wikipedia or the protein databases, known inhibitors, and putting those into our databases. And this is what the databases look like. And then we tried to, for as many of those compounds as we could, look to see what acute toxicity data were available by any route. And that actually worked, but it wasn't very efficient. And so we needed to go to Plan B. Well, Plan B happened when I got a postdoc, and I said, let's work on trying to make this more efficient. And here's another example of AOP. I threw this one in there for two reasons. We've done a lot of work modeling the 10K mitochondria data, as well as you're going to see me talk about scaffolds. Mark Cronin's group at John Livermore University, he's taking mitochondria and he's building a lot of the scaffolds. So you see the scaffolds are these substructures that are distinguishing interactions. Because his group is doing that, there was no sense in my group trying to do the same thing, because we can pull his scaffolds from his publications into our databases, and when we publish ours, as you'll see in a minute, they can do the same. And these are all publicly available, and the hope would be in my future slides down the road that there will be merit in others doing these for other targets, and then we'll have a big mechanistic database. So when we started doing what I just described for a number of specific mechanisms that we found precedents for looking at their involvement in acute toxicity, you see the list here. This list has been updated, but the slide hasn't. The difference between the blue and the black are blue are ones that off the top of my head, I I guessed if you had an in vitro assay that looked at basal cytotoxicity, that is, just is going to kill the cells or not, most cells, that these mechanisms would be captured by that. Those in black would not be, and these are more signaling pathways. And the importance for that is if you take a lot of the cytotox assays out there, for instance, from the Tox21 or ToxCat, you just take them and you try to model them versus acute toxicity without understanding what the mechanisms are, you're probably going to have some confounding based on the mechanism. And in fact, I had too many slides, so I dumped that one. We've done that, and you don't get good correlation. So our thought is, now that we're doing the scaffolding, we can pick a couple of these subsets of mechanisms and go back and see if we then, in a much more organized manner, try to do the same thing, whether it would work or not. I haven't done that yet. So when we were finished with that, we tried to simplify that table. And when it was simplified, we came up with 5 major classes. The first is not very simple at all. It's interaction with the receptors and enzymes. The reason I say it's not simple, there's 22,000 protein coatings in the mammalian, and so in here there's embedded 22,000 different subclasses. Hydrophobics, and this is the first one I showed. They non-specifically interact with proteins, membranes at some dose, usually a high dose. They'll just start shutting everything down. Chemically reactive compounds, we've derived our own profilers. The reason being, I try to use a bunch of the freeware to look at some of our databases, and I wasn't satisfied, so we just finished deriving our own for fast cell reactivity. Chelants and surfactants, these are actually trickier to spot than you might imagine, but if they can find their way, especially the chelants, to be systemically bioavailable, they can be highly acute and toxic. So then we applied the rest of our pathway here, because again, we were able to, I shouldn't say I got, a postdoc, Sanjeeva joined our group, and he came from UM with Rudy Richardson's lab, where they focused on cholinergics, and I thought that I would really allow him to build upon that what he had walking in the door. So the thought was, let's go and build our empire with him around the cholinergics. And so what we've been doing, and his major postdoctoral research right now, is focused on pulling the world's data in on cholinergics. And so I'll highlight what we've done with the nicotinic acetylcholine, which are cis loop receptors today. And we have over 4,000 that you'll see. We've also pulled data for the muscarinics. There's over 8,000. The acetylcholinesterase inhibitors, which are your OPs and carbamates. OPs alone, there's about 800. Carbamates, thousands. We're still working on pulling the carbamates on. And then we're assuming these will get grandfathered in the neuropathy target esterases and with the OPs. So I'm not artistic, but he said he was. So I took my rat and I asked him to start developing. We want to develop these. We picked a rat because we just happen to have one, pathways, where if you click on something in the pathway, any one of those 22,000 proteins, for instance, it'll actually pull in these databases. So when we asked them to draw the rat, you see what we have represented here, which would be the actual interaction with a nerve and a muscle cell. That acetylcholine comes from the nerve cell. It's inhibited by cholinesterase, and it can either bind to a nicotinic or muscarinic acetylcholine receptor, and that causes a downstream effect. And so we focus first on the nicotinic receptors, which are ligand-gated sodium channels, pentameric. These pentamers really vary based on age and evolution and organ, but extracellular membrane, intracellular. And if you can see here, nicotine, which is the quintessential identifier for the nicotinics, it binds between two of those pentamers. And we're trying to use docking, where we model the structure of the protein and we model the structure of the ligands. And when we do this, we take the proteins from our crystal databases for proteins, and where they'll actually crystallize it with the ligand. And when we show our dock pose versus the actual crystallize, they superimpose. So giving us some confidence that using this approach, in fact, would work. And then we pulled all this into a KNIME workflow, and the KNIME workflow involved gathering data, scaffolding those compounds, and analyzing and verifying the results. And as I mentioned, for the nicotinics, we have over 4,000 compounds that when we did this, none of these are Dow unless it's by chance, because we're pulling them from public databases. And we wouldn't actually know if they're Dow or not, quite honestly, the way we're approaching this. And then to scaffold these, this would be, what are substructures that would distinguish these? So conceptually, you could have 4,000 compounds and 4,000 scaffolds. Every compound's its own, but that's silly. So when he first came and we first cut, there was 1,000. I said, well, that's good, but that's still too many. And then I had him get it down to 100. And I said, that's reasonable. And I'll show you the scaffolds in another slide. But there's an art in doing that, and we ended up looking at some freeware that's out there, but because we're a .com, just so people realize, freeware that you'll see published that's free to a .edu or a .gov is not free to a .com. And so, and we have budgets just like everybody else. So something that costs $50,000 to me when I don't have that $50,000 in my budget, I'll instead challenge my postdoc, come up with our own version of this that we'll publish and make free, and it'll be free to anybody once we publish it that way. Not knocking, and I'm not trying to be anti-capitalist, but it is what it is. So when we did this, what we found is when you use these scaffolds, and then we took the ToxCast library, where this was an endpoint in ToxCast. So we took the compounds in ToxCast that were shown not to be involved in this pathway, and we challenged them with our scaffolds to see, would it flag them as being involved in the pathway or not? We had 99% confidence that if it told us they were not going to hit this target, they weren't hitting the target. And so when he came to me with that number, I said, that's way cool. And because we can start using these approaches then to start pointing, using scaffolding, if nothing else, to different mechanisms. And if we don't have enough tox data in vivo, we can then point to a real specific in vitro assay or a targeted in vitro assay might be able to use as a surrogate. So that's a big part of what we're trying to do with this scaffolding. And then we also thought, well, let's not stop there and let's use docking. And the way we did the docking was within the scaffolds. And I pulled it out of the slide, but to not use the scaffolds, if we just took these 4,000 compounds and you model them versus log KOW, the R squared was 0.000 is rigid. So it doesn't work. And because we tried it, we thought we'd be asked if we didn't try it. So we thought, let's look within the scaffolds and then develop statistical models within each of those. The other thing we did, here's the number of compounds we had, about 4,500. We docked all of them, except I can't remember, some of these were salts or something that we couldn't dock them all. A lot had in vitro functional assay data, and here's the, almost all had binding data. This is the breakdown of the binding data. These are the numbers of binding data, these are the breakdown of the functional. And the reason we are looking real closely at this, if we have to go work with the folks at NIEHS or NICEDM or ILS to develop high throughput assays, we're trying to understand what are the best high throughput assays to go and work on. And the sad part of this is there's hardly any in vivo data for the most data rich endpoint we have, which is acute tox. And so we're going to have to use these data to really ground everything else, but it is what it is. Here's the scaffolds, the major breakdown. I think we got it to 6 or so. And then looking at the R squareds, if we could model it with acute tox or we had enough, we did. And we also then within a scaffold, we looked at docking versus log KOW. Here, both were actually log KOW was a little bit better. Here, if we're trying to actually look at functional assay, log KOW didn't work, docking did. Same here with the nicotine dopamine release. Docking worked very well. Docking worked okay. Docking worked well, sorry for the typo. And then here, log KOW better, and calcium flux, docking looked better. So that's our approach in general. And the thought is to start building this empire of around the other targets. And right now it's a limited empire. We're going after the cholinergics. We're going to finish up the muscarinics and then start hopefully having dialogue with others that want to participate in this. Gathering the acute tox data, as I mentioned, to ground the in vitro and in silico models. Finish delineating the molecular initiating events. Define as many OPs for high acute tox as we can. Ultimately, you didn't hear me mention gene expression data, and there's a lot of data being generated, and in a few years, I think the ability to pull those in and start making sense of them will be more than it is now, so we've held off on that. Defining the best in vitro models, develop more collaborations, and then look more at bioavailability and metabolism. So thank you for your attention.